So to understand a little bit better how the solar system formed, astronomers have done a lot of simulations of the inner planets, how the inner planets formed. And that's done basically by, in this case, they start out with 100 planetesimals orbiting an object which has the mass like our sun. You see these little planetesimals and they're swirling around with velocities that keep them in orbits. And over time, if you let this simulation evolve, what happens is these planets start colliding and crisscrossing the paths, and they start bashing into each other and coalescing and accreting onto each other. And eventually, you wind up with, in this case of this simulation, you wind up with four objects, just like the four rocky inner planets that we find in our solar system. And they reach stable orbits which don't intersect, and you have a simulation that produces, in this case, a situation very similar to our solar system. So there's a lot of work that's actually done to try to simulate how you start from a lot of objects which are small, aggregating, accreting, and forming what we see today. And it can be done, and it can be done. All right, so let's look at, it's hard to really produce images and that really capture what is thought to have happened in the early solar system. So there's a pretty good video here. So it's a Stephen Hawking video. Let's take a look at this and see a little bit about the formation of the solar system. All right.
Our solar system, the place we call home, lies about 26,000 light years from the center of our galaxy, the Milky Way. Or around two-thirds the way up. The story of how these huge planets came to be orbiting an average yellow star is 6 billion years long. And since we don't have that much time, I'll speed it up a bit. It starts with a bang. Long ago, an ancient star exploded, littering space with swirling clouds of the materials it had made while it lived, and the heavier metals it created as it died. We know this because we can see similar fields of dust out in space today. They are called nebulae, and they are very beautiful. Every nebula is different, and in our case, the clouds contained nitrogen and oxygen and iron and silica and all the other stuff needed to build a world like ours. Then the tireless force of gravity started to pull it all back together, and the heavy engineering that produces planets began. Vast spirals of dust began to form, and at the center of one of these, a rocky planet called Earth started to take shape. Built of stardust and assembled by gravity. Fast forward 100 million years, and it had grown into a giant ball, sweeping up millions of tons of celestial debris. This is where the Earth came from, and therefore how you and I began. But our planet would have remained a large, sterile ball of rock and metals, minerals forever, were it not for one more event, one more expression of the forces of nature. 93 million miles away, at the heart of the giant nebula, the pressure and temperature of a ball of hydrogen gas had become so great that the atoms were beginning to fuse. A new star, our sun, was coming to life. As the sun ignited, it gave off a huge blast of solar wind, a radioactive gust of energy. This blew all the remaining dust and gas that was left downward from the nebula out to the edge of the solar system, which is why everything is nice and orderly today. In the outer reaches of the solar system, we have the huge gas planets, Jupiter, Saturn, Uranus, and Neptune. Further in are the denser, rockier planets, Mercury, Venus, Mars, and of course, the Earth. Lucky for us, the Sun is 865,000 miles in diameter, or just the right size to burn consistently for a very long time. 8 billion years, long enough to allow the next development to take place. Life.
Okay, so that's pretty cool graphics on that. Um, all right, so let's move on. So, okay, just sort of reviewing the protoplanets when they form by accretion, form together. You have the four what are called terrestrial planets, the rocky planets: Mercury, Venus, Earth, and then Mars. Okay, and they're primarily silicates, and of course there's water on Earth, but they're denser elements than hydrogen and helium gas, and they're solidified. And then you have the Jovian planets. So they're Jovian planets are all the four outer gaseous planets, which are much colder and much bigger. Have an incredible amount of hydrogen and helium gas, which the inner planets don't have, and that's Jupiter, Saturn, Uranus, and Neptune. So there's two distinct, as we talked about at the very beginning, there's two distinct types of planets. Now, how can this be? And one of the reasons why there's such a difference between the smaller rocky planets and the outer gaseous planets has to do with where they are positioned relative to the sun. So in this image here, you can see here's the proto-sun, and when the sun formed, basically regions that are close into the sun, extending out beyond Mars here, it's going to be warmer. There's a lot more light. Of course, it's much hotter at Mercury, and it cools off as you move out towards Earth and Mars, and it gets colder and colder as you go further out. So it's very warm. One effect of this is when there was original nebula, which included gas all around, gas in all regions far out, was that the gas, hydrogen, helium, stayed in gaseous form, and it's very difficult for gas to be accreted, to be affected by gravity. It's so light, moving so fast. It's very difficult for it to be attracted to planets. Basically, if they're small, it's hard for them to absorb a lot of gas, and so they wind up absorbing the heavier elements, which are solidified at these warm temperatures, and you wind up with rocky planets. On the other hand, if you go much further out, there's this demarcation line, which is so-called the frost line. So the frost line is out here, which is out close to where Jupiter is. And on this frost line, it's actually cold enough. You're very far, it's about 5 AU, listed here, it's 5 AU. So 5 times the Earth's sun distance, so it's almost 500 million miles out from the sun. There's so little light, it's so cold, that the gas that was part of the original nebula actually will stay in liquid form. You actually have solidified form or liquid form. So it's heavier than a gas. So the gas molecules can condense into liquids, and they can form compounds like water, ammonia, and methane, and other things. And because they're larger, it's much easier for these elements then to be attracted to planets. And so what happens is it's cold out here, and the gases become much denser, and they're able to accrete onto these protoplanets. So that's essentially why these outer planets were able to absorb all of this hydrogen and helium and water and ammonia and other gaseous elements onto them, whereas the inner planets couldn't. It was simply too hot, and the gases could not be attracted to to the planets. Okay, so let's talk a little bit more about what happens, and it showed in the video a little bit, what happened after the planets were formed. Why Why isn't there gas everywhere still, gas that has not been absorbed on the planets? Well, part is when the sun, as it mentioned, when the sun started producing lots of energy and lots of heat was coming off the sun, a lot of material was there, and fusion was going on, as we'll talk about later. But essentially, the sun creates the heat and the radiation from the sun over long periods of time. The light and radiation coming out from the sun can actually push gases out away from the sun. It actually pushes the gas far away. And that sort of cleared out the dilute gas that was permeating all between the planets. There's some other things that there's a period, we'll talk some more about this when we discuss the moon, which is coming up shortly, is that the sort of last phase where the planets were forming was called the late heavy bombardment. And that time is when it's 500-600 million years after the original formation of the planets as they really started taking shape, and there was still a lot of meteors, still a lot of asteroids swirling around the solar system, and they wound up colliding, and you can still see evidence of that. A lot of the craters on the moon come from this period, and a lot of the last sort of large elements, large planetesimals and large asteroids were being absorbed onto the planets that were forming. And so that helped clear out the nebula, clear out the regions between the planets. And the other thing is that the effect of Jupiter and Saturn. Jupiter and Saturn are enormous planets. They have a tremendous amount of gravity between them, and it's their interactions as they rotated around the sun. They were able to slingshot things that were formed near them into orbits that moved them out beyond the solar system. And we'll talk a little bit more about that coming up. So one other important thing, it's interesting if you look back, and we'll show this, if you look back at the original picture with the 4 inner planets and then you have the gaseous planets, there's actually a big gap between the last inner planet, which is Mars, the rocky planet, and the first gaseous planet, Jupiter. It's actually quite a large gap where there's no planet at all, but there is a lot of material there. There's a lot of material in the form of rocky asteroids, and that region is called the asteroid belt. And in fact, there would have been another planet there. There's enough material, there has been enough material that is swirling around in the asteroid belt to form a small planet. But because of the gravitational effect of Jupiter, it's quite close, relatively speaking, close to Jupiter, that Jupiter's gravity sort of pulls on and tugs on all these asteroids flying around and prevents them from sort of coalescing, aggregating to form another planet, or a ninth planet. Okay, so you just sort of take a review here of what we had. We started out by saying originally there was a gas cloud, which is a nebula, which is the result of a dying star. And in the case of our solar system, it was the case not of a planetary nebula from a low-mass star, but actually from it's thought that it's from a supernova, because we have a lot of supernova produced. That's the rapid explosion of a very, very heavy star. And that actually produces a lot of heavy elements. By heavy, I mean things like gold, even iron, uranium. These very, very heavy elements can really only be produced in supernova explosions. And they do exist in our solar system, and so it's thought that that's the origin of the original gas cloud. And that gas cloud, as we talked about, it will swirling gas cloud that forms a spinning disk of a lot of dust and debris, and then over tens of millions of years that starts to coalesce together into regions where there's a lot of asteroids, a lot of planetesimals, small planets, and these things begin to aggregate into planets that are then orbiting the sun. And here we have what's called, you can sort of see here, the snow line, the frost line, inside of which basically gases cannot really be absorbed by planets, and outside, since the gas condenses into a liquid or even a solid, it's cold enough, then it can, and that caused the growth of very, very large planets, very, very large planets outside. Okay, go on to the next chapter in a minute.